Okay, so welcome back to section 7, or actually welcome to section 7.6, not welcome back, but welcome to section 7.6. In section 7.6, we're going to be taking a look at something called Bayes' Theorem. In fact, that's the only objective we have here. Bayes' Theorem. Okay, so start out. Bayes' Theorem is arguably one of the most important probability theorems out there. And the reason being is that Bayes' Theorem is incredibly powerful because it gives light to something that is very counterintuitive for people. Okay? We're going to start by taking a look at an example and show you how Bayes' Theorem comes into this. Okay? So here's our example. Suppose that 1/3 of the applicants for a job are qualified by having enough experience, qualified by experience, and the rest are qualified by education. So they have a certification or something in that. Right? Further, suppose that of the qualified by experience individuals, 10% advance to the interview level of the hiring process, while only 5% move on. Those 5% of those are qualified by education. So I've got a couple of probabilities here. I've got 1/3 of the applicants are qualified by experience, and then the rest, meaning 2/3, are going to be qualified by education. So I'm going to start drawing a tree diagram down here to set this out. Okay? And so we have people that get there by their experience, and we get people who get there by their education. The probability that an applicant got there by experience will be 1/3, and then of course then that 2/3 would be that probability they got there by their education. Okay? So if I were just to run down to the HR department and just grab all of the applicants for the job, 1/3 of them experience, 2/3 of them education. But then we screen them, and some of these people go on to the interview, given that they got there by their experience, and some of these people don't get an interview, given that they got there by their experience. Okay? Some of these people down here will get to the interview, given that they got there by their education, and some won't get an interview, given that they got there by their education. Right? Now the problem tells me that this is a 0.1%, 10%. That means that 90% of those people don't make it, and this was 5%, which means that 95% of those people don't make it. Right? So there's my tree diagram for this scenario. And so now I'm going to look at what they actually want me to calculate. If a randomly chosen interviewee is selected, what is the probability they are qualified by experience? What is the probability they are qualified by experience given that they made it to the interview process? Now I want you to take a look at what's going on here. The probability that they want us to calculate is a conditional probability, but it's the flip of the conditional probabilities that are given in the information, the setup of the problem. They want us to change the direction. All of the information that we know over here in this tree diagram about the interview process is dependent upon, is given based on whether they did or did not have experience. And now they want us to flip the script and say, what's the probability that someone who made it to the interview process, so we know that they got interviewed, got there by experience? Right. Now the incorrect assumption would say that's 10%, but it's not. So let's take a look at what that's going to be. Now it's really, really hard to do these problems without having some sort of formula to work with. Well, let's just see if we can think about this for a second. Right? All right, so I'm going to erase this because I'm going to need this space, but we'll come back to it. I'm just going to move it down here to the bottom. I'm going to say the probability that they got there by experience, given that they got an interview, is. And I'm going to come back up here and I'm going to take a look at what each of these branches means. Now the product formula, or the product formula tells me that this branch is going to be the intersection of experience and interview, and that the probability for experience intersection interview is going to be the 1/3 times the 0.1. So 1/3 times 0.1, 0.03 repeating. So 0.03 repeating. This one is going to be the intersection of experience and I didn't get the interview. And so our probability here will be the 1/3 times the 0.9. So 1/3 times 0.9, 0.3. Okay, so 0.3. This one down here is going to be the intersection of education and got an interview. And that's going to be the 2/3 times the 0.5. So I'll grab my calculator. So 2/3 times 0.5. That's the 0.3 repeating. And then the last one down here is going to be the intersection of education, intersection didn't get an interview. And so that's going to be the 2/3 times the 0.95. So that's going to be 2/3 times 0.95. And that's going to be 0.63 repeating. So 0.63 repeating. And now if we were to add all those up, that would add up to 100%. And so now my job is to find the probability of experience given, what's that one? Oh yeah, the interview. Now if I tried to use the product formula for this, it would say something along the lines of, where's that product formula for before? It would say something along the lines of this. Probability of E intersection F is equal to the probability of E times the probability of F given E. Oh, but wait, this is a conditional probability. So I'm supposed to do the conditional probability form, which would be the probability of experience intersection interview divided by the probability of interview. Well, experience intersection interview, that's this one up here. So I know that my numerator is going to be 0.03 repeating. And then my denominator is the probability of interview. Well, probability of interview is this one and that one. So that's going to be the 0.03 repeating plus the 0.3 repeating. Okay. So that's going to be 0.03 repeating divided by 0.36 repeating. And then I'm going to have to try to figure out what that's equal to. So I'm going to grab my calculator. And I'm going to say, where's the 0.03? That was that one, right? So that's that. So let me grab that. And I'm going to divide that by the quantity. And I'm going to go back and grab that number again because I'm lazy. Plus the 0.3 repeating, that one. And I get 0.090909. So it looks like it's 0.09 repeating. Oh wait, that 8 on the end makes it not that. So we'll just round it to 2 decimal places and call it 0.09 or 9%. All right, so let's look and try to see what this means. 1/3 of the applicants are qualified by experience. 2/3 are qualified by education. 10% if you got there by experience, got an interview. 90% didn't get an interview. 5% get an interview if you got there by education. 95% don't. If I walk into the interview room, which is only full of people who got an interview, and I say, what's the probability that they got there by having experience? Well, the probability of experience, given that you made it to the interview, is going to be 9%. So what does that mean for these people? Well, it looks like it means that 91% of the people who were interviewed got there by having an education rather than having by an experience. So this is conditional probability. Conditional probability is this idea that something happens and we know a prior event, right? Bayes' theorem builds on that and says, what happens if you want to change the direction, if you want to change the order of the conditional probability? So everything in this problem, all of this stuff up here where it says further blah, 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 blah business, all of that is conditional probability, but it's all the conditional probability about getting an interview if we know that you have experience, or getting an interview if we know that you have an education. The question that they want to know the answer to is the flip of that. The probability that if you got an interview, that you got there by experience. And so what Bayes' theorem does is Bayes' theorem takes conditional probability and allows you to change the direction of the conditional probability, change which event happens first and then which event happens second. Bayes' theorem. The probability of f given E is equal to the probability of f times the probability of E given f divided by the probability of f times the probability of E given f plus the probability of f complement times the probability of E given f complement. Now, believe it or not, that is that right there. So let's take a look at where those numbers came from, right? Now, this formula down here, I don't want that. This formula down here is written with E's and F's, but if I were to rewrite it using our stuff, the probability of experience given interview, so that's going to be our F, and that's going to be the E in the formula, because that's the left-hand side, is equal to the probability of experience times the probability of interview given experience divided by, well, if you look, that is the same thing as that, right? So the probability of experience times the probability of interview given experience plus F complement. Well, if F is experience, then F complement is education. So the probability of education times the probability of interview given education. And now if I go back to my tree diagram, do you see how my numerator here is that branch right there? And then my denominator is that green branch again, along with education interview, which is our 0.3. So Bayes' theorem. Bayes' theorem allows us to take conditional probability and change the direction of it. Now, why is this called the special case of Bayes' theorem? Well, what it should be called is the least complicated version of Bayes' theorem, because this is Bayes' theorem in general. Bayes' theorem says that if you have a conditional probability that you wish to have calculated, that to find that, you have to do this formula right here. And what this allows us for is this allows us to have one event E in the second stage of the experiment, but many events F1, F2, F3, F4, F5, F6, Fn in the first stage. So our tree diagram could look like this. So there's F1, and then there's F2, and then there's F3, and then there's F4, and so on and so forth. But the second stage can only have E and not E in it, because there's only allowed to have two options, but one event. Either it occurred or it didn't occur in that second stage. And that's actually Bayes' theorem. We have the simple version, if you want to call that, the least complicated version of Bayes' theorem, because we only have that one event in the first stage. It either occurs or it doesn't occur. So 2 branches. Right. Using Bayes' theorem, do what we just did. Draw a tree diagram, label each branch, find the branches that matter, put it all together into the proper format, and then do a whole bunch of arithmetic. Let's take a look at an example here. A manufacturer buys from 6 different suppliers. The fraction of the total number of items obtained from each supplier, along with the probability that an item purchased from that supplier is defective, is shown in the following table. Right? Find the probability that a defective item came from supplier 5. So do you see how this is going to represent those F's? And then this is going to be the E in that Bayes' theorem formula. All right, so what I'm going to do is I am going to attempt to draw the tree diagram for this one. Now it said to draw the tree diagram, start by 1, 2, 3, 4, 5, 6. And so in terms of Bayes' theorem, those are our possibilities for that first stage of the experiment. That's our F. So if you want to get fancy about it, we could say that that's F1, that's F2, that's F3, that's F4, that's F5, that's F6. And those have given probabilities, 0.05, 0.12, 0.16, 0.23, 0.35, and 0.09. And then we've got that it's either defective given that it came from 1, or not defective given that it came from 1, or defective given that it came from 2, or not defective given that it came from 2, or defective given that it came from 3, or not defective that it came from 3, or defective given that it came from 4, or not defective that it given that it came from 4, or defective given that it came from 5, or not defective given that it came from 5, or defective given that it came from 6, or not defective given that it came from 6. And then each of those is going to get a probability based on that second column. Like this is 0.04, that means that this one's 0.96. And then this one's 0.02, and this one's 0.98. And this one's 0.07, and that one's 0.93, and 0.01, and 0.99, and 0.03, and 0.97, and 0.05, and 0.95. And then they want us to find the probability that the item is defective given that it came from supplier 5. So according to Bayes' theorem, that's going to be the probability that it came from 5 times the probability of being defective given that it came from 5, divided by, and down here, I'm going to have the probability of 1 times probability of defective given 1, plus the probability of 2 times the probability of defective given 2, plus the probability of 3 times the probability of defective given 3, all the way out to the probability of 6 times the probability of defective given 6. So in terms of the math, I'm going to have upstairs, probability that came from supplier 5 is 0.35 times 0.03, and that's this branch of the tree diagram right here. And then downstairs is going to be every single branch that terminates in defective. And so it's going to be 0.05 times 0.04 plus 0.12 times 0.02 plus 0.16 times 0.07 plus 0.23 times 0.01 plus 0.35 times 0.03 plus 0.09 times 0.05. And if you're wondering how I'm doing that so quickly, I'm actually reading it right off of here, because those are the branches. And then calculate all that. So then I got to calculate what that works out to be. So that is absolutely a calculator problem. So I'm going to make a fraction. My numerator is going to be 0.35 times 0.03. My denominator is going to be 0.3. Oh, wait. I'll start with the first one. 0.05 times 0.04 plus 0.12 times 0.02 plus 0.16 times 0.07 plus 0.23 times 0.01 plus 0.35 times 0.03 plus 0.09 times 0.05, and I get so the probability that an item that we know to be defective came from supplier 5. So the probability of defective, given that it came from supplier 5, I have that written backwards. This should be 5 given defective. I don't know why I wrote that backwards. I'm so sorry. I'm sure that at least one person was out there going, hey, wait a second, why are you writing it that way? Is 31.9% or almost 32%. So if I walk down to the defective item pile and I grab something out of there, there's a 32% chance that it came from supplier 5. Now the reason that people argue that Bayes' theorem is so powerful is because this number that we just found is so different from anything up here that it feels counterintuitive. How can there be a 32% chance that something came from supplier 5 when there's only a 3% chance that their stuff is defective? Well, there's a pretty good chance the stuff came from supplier 5 to begin with, because they supply 35% of our goods. So that would make sense to say that of the defective stuff, they should have a big chunk of it, even though their individual probability for defective is low. Let's take a look at another example. See if we can make sense of this one too. Okay, so here we go. Suppose that the probability that an individual student will pass a math class is 80% if they complete the review packet, but only 65% if they do not complete the review packet. Well, those are going to be conditional probability statements because they are pass the class based on some prior activity, in this case, doing a review packet. Okay? Further assume that only 60% of the class completes the review packet. Well, that's just a plain old probability. And then they want us to calculate some probabilities here. What is the probability of the individual who passed the exam, completed the review packet? And what is the probability that an individual who did not pass the exam did not complete the review packet? All right, so first things first, I'm going to draw my tree diagram. Okay? And I have review packet and did not complete the review packet. 60%, so 0.6, 40%, so 0.4. Now, once we have the review packet, you either pass the exam, given that you did the review packet, or you do not pass the exam, given that you did the review packet. You can pass the exam given that you didn't do the review packet, or you cannot pass the exam given that you didn't do the review packet. 80% pass the exam when they do the review packet, so that means that 20% don't. 60% pass the exam, 65% pass the exam if they don't complete the review packet, and 35% don't. Okay. The first probability they want me to calculate here is what is the probability that the individual who passed the exam completed the review packet. So what's the probability that you completed the review packet if we know that you passed the exam? So right there I know it's Bayes' theorem because they're asking me to find the inverse of a probability that has been given in the problem. They want me to find the inverse of that one right there. Okay? So according to Bayes' theorem, that's going to be the probability of the review packet times the probability that you passed given the review packet, divided by all the different ways you can pass the exam. Well, there's only one other branch that passes the exam. It's that one. So it's going to be the probability of review times the probability of pass given review, plus the probability of review complement times the probability of passing given review complement. So it's going to be 0.6 times 0.8 in my numerator, divided by 0.6 times 0.8 plus 0.4 times 0.65. Math, calculator, clear. Going to make a fraction again. My numerator is going to be 0.6 times 0.8. My denominator is going to be 0.6 times 0.8 plus 0.4 times 0.65. Oops, there's a mistake. You see it? Let me fix that real quick. 0.4 times 0.65, and I get a 65%. So what does this tell me about this situation? Well, this tells me that if I go into the pile of people who I know passed the exam, there's a 65% chance that you did the review packet. Right? The second question is asking something different. What's that second question asking? It's asking, what is the probability that an individual who did not pass the exam did not complete the review packet? What's the probability you didn't do the review packet given that you did not pass the exam? Well, according to Bayes' theorem, that's going to be the probability that you didn't do the review packet times the probability that you didn't pass the exam given that you didn't do the review packet, divided by all the ways you can not pass the exam. So that's going to be, let's see, the probability of R complement times the probability of P complement given R complement plus the probability of R did the review packet times the probability that you didn't pass given the review packet. In terms of numbers, that's going to be, let's see, the probability of R complement is 0.4 times the probability of not passing is 0.35 divided by 0.4 times 0.35 plus that business, so 0.6 times 0.2. Math, calculator, clear. Making a fraction. My numerator is 0.4 times 0.35. My denominator is going to be that 0.4 times that 0.35 again, plus the other way to not pass, which would be 0.6 times 0.2, meaning you did the review packet but didn't pass. And I get a 0.538, so 54%, round wherever they would tell me to round it, so I can make that look a little prettier there. 538. So about a 54% chance. And so what is that attempting to tell me? Well, if I go into the pile of people that I know didn't pass the exam, and I randomly select a paper, there's a 54% chance that they did not do the review packet, given that they did not pass the exam. Okay? Now, these are a couple of examples of Bayes' theorem, but I would like to do a couple more because there are some that make this much more powerful, but we're already at 29 minutes, so I'm going to stop this video here, and I'll come back and we'll do a couple more Bayes' theorem.